Hi, let us study today about equivalence relation. A relation R in a set A is said to be an equivalence relation if R is reflexive, symmetric and transitive. Let a capital L be the set of all lines in a plane and a capital R be the relation defined as R is equal to the set of all L1, L2 such that L1 is parallel to L2. Show that it is an equivalence relation. What is the meaning of the given relation? Now let us consider A and B. A, B are parallel here, hence they are related. Now you consider P and Q. Also P and Q are parallel, so they are related. Now consider R and C. They are not parallel, therefore they are not related. So R and C is not related. Now let us check the reflexivity. Here line A is parallel to itself and hence A is related to itself. Similarly, line B is related to itself. Why? Because line B is parallel to itself. Line P is related to itself. Similarly, line C is related to itself. Thus, we must see that every element of set L is related to itself, showing that R is reflexive. Now we shall deal with the symmetry. We see that A is parallel to B. Also, we may see that B is parallel to A also. That is, A is related to B implies B is related to A. Now consider P and Q. P is related to Q implies Q is related to P also. Thus, whenever A is related to B, we see that B is related to A also. Hence, the given relation is symmetric. Now for transitivity. A is related to B as they are parallel. Now also we see that B is related to C. From this, can we claim that A is related to C? Yes, we can. Why? Because A is parallel to C. Thus, A related to B and B related to C implies that A related to C. Hence, the given relation is a transitive. Once again, P is related to Q, and Q is related to R, and we see that P is related to R. Hence, transitive. Thus, we see that the given relation is reflexive, symmetric, and transitive. Hence, it is an equivalence relation. Let us consider another example. Let L be the set of all lines in a plane and R be the relation in capital L defined as capital R is equal to the set of all ordered pair L1, L2 such that L1 is perpendicular to L2. Show that R is symmetric but neither reflexive nor transitive. Let us consider the set of all lines in a plane. Our L is the set of all lines in a plane. What is the meaning of the given relation? Here, the lines A and B are related as they are perpendicular. Similarly, we may see that P and Q are related as they are perpendicular. But R and C are not perpendicular, means they are not related. Now consider the line D. It is not perpendicular to itself. Thus, D is not related to D. Hence, the given relation is not reflexive. Now let us check symmetry. We see that A is related to B means A is perpendicular to B, and we see that B is perpendicular to A also. Hence, B is related to A. Similarly, P related to Q implies Q related to P. Hence, the given relation is symmetric. Now, let us check whether the given relation is transitive. Line A is related to B as they are perpendicular. Also, line B and C are related as they are perpendicular. But lines A and C are not perpendicular, and you see they are parallel. Thus, the given relation is not transitive. Thus, we see that the given relation is symmetric, but neither reflexive nor transitive. Let us consider another example. Let C be the set of all students in a class, and capital R be the relation in capital A defined by capital R is equal to the set of all ordered per AB sets that A and B are of the same height. Show that capital R is an equivalence relation. Let us consider some students of the class, say A, B, C, D, E, F, G. What about the given relation? Here students A and C are related as they are of same height. Consider the students E and G. They are related as their heights are equal. Now the students E and F are not related because their heights are unequal. Let us check whether R is reflexive. For example, B is related to B. Similarly, we see that C is related to C. Now consider the student D. And D is related to D and so on. Thus, we see that every student capital A is related to A. So, R is reflexive. Now B is related to D and D is related to B also. Similarly, C related to F implies that F is related to C. Thus, whenever A related to B, here we claim that B related to A also. Thus, the given relation is symmetric. Now for transitivity, B related to D and D is related to E, and it implies that B is related to E as they are of same height. Thus, the relation R is transitive also. Thus, we see that R is reflexive, symmetric and transitive. Hence, R is an equivalence relation. One more example, this time with numbers. Show that the relation capital R in the set Z of integers given by R is equal to the set of all AB where 2 divides A minus B is an equivalence relation. What do you mean by this relation? 7 related to 3. Why? 2 divides 7 minus 3. That is 4 is divisible by 2. And 5 is not related to 4 because 5 minus 4, that is 1 is not divisible by 2. Now let us consider any integer, say 3, and 3 minus 3 equals 0, which is divisible by 2. Thus 3 is related to 3. Similarly, 4 related to 4, negative 5 related to negative 5, and so on. Thus, the given relation is reflexive as 2 divides A minus A is equal to 0 for all A belongs to Z. Now, 7 related to 3 implies that 2 divides 7 minus 3, which implies 2 divides 3 minus 7 also. That is, 3 is related to 7. Thus, 7 related to 3 implies 3 related to 7. Similarly, 8 related to 20 implies 20 related to 8 also. That is, if ordered per AB belongs to R, then 2 divides A minus B. Therefore, 2 divides B minus A, which implies BA belongs to R, which shows that R is symmetric. Now for transitivity. 3 related to 7 and 7 related to 15. From this, we may conclude that 3 related to 15 as 2 divides negative 12. Thus, if AB belongs to R and BC belongs to R, then A minus B and B minus C are divisible by 2. Now A minus C is equal to A minus B plus B minus C, which is even, because the sum of two even numbers is also even. So A minus C is divisible by 2. This shows that R is a transitive. Thus R is reflexive, symmetric and transitive. Hence R is an equivalence relation in Z. Thus, a relation which is reflexive, symmetric and transitive, that is what is called an equivalence relation.